For the tutorial for ship, okay, we are going to use the same solver as used in dam break. So I will only highlight the additional features that is used for this case. Other than that, it is similar to dam break. Okay. So again, for this case, we uh, try to uh, separate into similar steps. Okay. Here I need to clean everything first. Solving configurations post wrapping. Okay. All right. So for for the tutorial that is very relevant for our case, we will look at tutorial under multi-phase flow, and then under interflow. Okay, we are going to use the same solver. Then just now we use laminar flow, right? But for ships we use Reynolds average turbulence modeling. So our particular attention is DTC hull and also DTC hull moving. This is 0 DOF, and this one it is 2 DOF. Okay, and the setting is very much the same. Okay, you can try to compare this using a tool. Okay, I'm using meld. Okay, I'm using meld, so you can check the difference. Okay, for moving, this is how moving, you have dynamic mesh. Okay, because you have motion, then you need to specify the mesh motion. Okay, and then control D, okay, then you need to adjust. Okay, because for DTC hull you can use steady model, but for this hull moving you need to use transient model. Okay, the schemes are a bit different. Okay, local Euler only suitable for steady case. Euler method for time scheme needs proper transient punya ni. Tapi biasa satu je tak banyak. Okay, and then have the solution. You can see the difference. Try to check for yourself and ask. You can ask AI to explain to you bit by bit. Okay, and a bit different in, I think, snappy smash here. Okay, and finally we have a run. A run is also a bit different. Okay, you can use the tool like melt to study the difference. Okay, so anyway we need to begin with the TCL first, so I will copy this, then paste it outside of the tutorial folder. Okay, I don't want to mess up with the default configuration if I do mistakes. Okay, so this is DTC hull. Okay, so here I am going to remove all of the previous bash sessions. Okay, and I want to create a new session under DTC hull. Then I load up my OpenFOAM environment. Okay, there. Okay, let us investigate. Okay, now for this this particular problem, now you have a much more number of variables to manage. Okay, constant, you have href to to as a reference for your water level. And then here you have additional settings, okay, but we focus on the additional features that we use for this particular problem. Okay, so again, we use DTC hull case. And this is our case files. Okay, here again you have a zero origin folder, and we have constant, and again we have system. If you do this many times, you can see the same pattern. We only need to change some small value. And we also have all run and all clean. Okay, all run and all clean. Okay, so this is scripts that helps you go through all of the operations that are required. So for example here, now just now we have 3 steps. This time we need to copy first the geometry, and then you get some surface features. Okay, we set some surface features. You create a block mesh. Okay, you have a block of mesh, and then you can apply the shapes of your ship using SnappyX mesh. Okay, next you set fields for the initial condition for the fluid phase, and you want to run on parallel cores. Let's say your computer have 8 cores, and you can run it on, let's say, 8 or 4 cores to make sure that your simulation finish faster. Okay, then you run the application, the interform. So let me change it directly for you. Interform. Okay, then after you finish with running the multi-phase, the parallel simulation, then you could combine them together. Okay, so let us start from the beginning. Okay, so CPF, first you need to copy the file. You need to copy. Okay, you can ask again, you can ask AI to explain what this one does for you. Okay, CP means copy. Okay, this one you create a folder named constant entry surface. Okay, I can comment. Okay, so I can disable other things by setting this up as a comment. So if I put 3 quotes here and 3 quotes down here, meaning I treat all of this as a comment, so this one will not run. Okay, so if I run this file, I'll run, I will create a 3 surface folder. Okay, now inside constant, we still don't have yet. Okay, so if you run this line, okay, and now we have a new folder, 3 surface. Okay, so this part is already run. Okay, this one not yet run. So next step, if we want to copy the file for DTC hull. Okay, so it is located inside resource geometry. Okay, I can just run this line. Okay, so I save this file and I'll run. Okay, so this specific geometry file will be copied into the destination, which is under constant and tree surface. Okay, so the new file should appear under this tree surface. Okay, so now I run the script again. Okay, now you can see that we already have this file. Okay, now I cannot display it. I need to extract it first. If I want to display this, I need to extract. I have this file. So this file I can open it up using some extension inside Visual VS Code. This is the file. Or you can use ParaView. You can use ParaView. Here I can run ParaView, and I can open the STL file to inspect. Open. It is inside constant, tree surface, and DPC script. Then if I press apply, and now I have the. So this is a STL format. STL format means it consists of small triangles to form the surface. Okay, so you must make sure that your STL file is fully closed. Okay, if it has some leaking, then you might have problem when you run the simulation. Okay, so you can expect. You can check the length, for example. I can display axis grid in order to see the length of the body. Okay, so here I can see that the length is around 6 meter. 6 meter. Okay, thickness is around 0.5 meter. Okay, then I can close, or maybe I just keep it this one around. No, I'm going to close it. Okay, okay, now we have finished with this file, so I can move this one up. Okay, so to make it seem easy, I can press alternate button on your keyboard and press up. Okay, okay, now I want to run the next step, which is surface feature extract. Okay, surface feature extract. What is surface feature extract? Okay, it is something you want to extract. Let's say if there are sharp edges on your body. Okay, there are some sharp edges on your body. Surface feature extract can extract it for you lah. So let's say you want the sharp surface features to be refined. You have a mesh that refined in that location. Okay, so what is it in general? Execute applications. Okay, not this one. Okay, this one is open form utility to analyze surface geometry. Okay, to identify significant geometric features. And how you can control it? You can check system and this one. Okay, so basically when the angle between two triangles is less than 150 degree, meaning ada shape lah, so you want to store it as an object. Okay, so here, okay, let me run this particular command. Okay, I save it, run. Okay, check that this one runs successfully. Okay, yes, okay, until the end. And now you have this image. This image is something that is generated. Okay, I'm not sure whether we can display this, but let's try. ParaView. close, file, open, constant. This, I think this one. Okay, this is all the features that has been extracted. Okay, if I apply, and this is all of the body lah. Okay, the features. Okay, I can compare it with the STL file. I think that the drawing is not so accurate, but basically you can see that the surface features included is basically along the sharp edges of the hull. Okay, along the sharp edges. Okay, it will be used to help in mesh refinement. Okay. Okay. So next step is block mesh. Okay. Next step is block mesh. Block mesh. We have will be based on this dictionary. Okay. As you can see here, you have 5 blocks. Okay, 5 blocks. Okay, 6 blocks. 6 blocks. Okay. Why with specific resolution in X, Y, and Z direction. Okay, so you can investigate what happened by running this block mesh lah. Okay, so I can save this file and then I'll run. Okay, wait a bit. Okay, now you have block mesh. Block mesh with how many cells? Okay, 134,000. Okay. So now you can again inspect your mesh. Okay. Powerful. So make it a practice. Run line by line and see what happened. Okay. You can change bit by bit and see what happened. Okay, this is our mesh created. Block mesh using block mesh. I can check the arrangement. Okay, so if you investigate this carefully, you can see that we have 6 blocks. So the first block is from the top to this location, and then second block is from here to here. The third block is for the water level meshing. Okay, fourth block down, and then you have a mesh at the bottom. Okay, this is the background mesh that we are going to further refine and refine. Okay, next, after you have your block, the background mesh defined, okay, next we create refinement, mesh refinement. Okay, using this construct. Okay, so this is a construct for a loop. A construct for a loop from 1 to 6. So basically this will run application, okay, number 1, and we will select. Okay, we will select some region using file topo set dict 1. Okay, so what happened is, okay, inside topo set dict we will select, okay, with name CO, cell set. You will select the cell inside this box. Okay, cell inside this box. This is the outermost box. Okay, okay, see what happened. Let's say I just run this line up until 1. Okay, up up until 1. And then I need to repeat everything from the beginning. Okay, so before that, I need to clean first my case, or clean. Okay, so here for the first loop, okay, we will run topo set dict 1, where it will select cell inside this box coordinate, okay, first corner and second corner, and then it will do refinement. Okay, it will do refinement on the selected cells. Okay, so the refinement specification is like this. It will only define in x and y direction, but not z. X and y direction. Okay, but not z. So if you run this, or clean, or all run, okay, I think it will appear here. Then you refresh your mesh. Press F5. It is okay. Now you can see the first refinement region here. It is actually inside this region. Okay, you can see that the mesh is refined in x direction and also y direction. You can use slice to this one. You can use slice to check check the refinement in y direction. Let's say I bring it up here, and then if I press apply, okay, and then for this part I want to display. So you can see here that inside the box you have a first level refinement. Okay, and then next we try to check what happened if we allow up until second level of refinement. Okay, save. Let me save. Then first I need to all clean, all run. Okay, and then if I refresh the data, F5, this is the second box. Okay, so please check. I think the mesh, if you want to apply to other kind of hull, this is the very important part. Okay, you need to control. Okay, so this is the box for the outer mesh for first level refinement. This is the box for second level refinement. Okay, and then you can see that for the third, and you can see that the box is smaller and smaller. Okay, smaller, and it's getting small. Okay, up until the sixth level. Okay, so if you allow the refinement level to proceed up to sixth level of refinement, you can have, let me clean first before I rerun. It is longer and longer because you have a higher count of cells. Have to wait a bit more. Okay, finish. You can see all of the log. Finish up until 6. Okay, Then you can check the statistic of your mesh by running block mesh, check mesh. Okay, so you have around how many cells? Now you have 900,000 cells, almost 1 million. Okay, here you can refresh the data reading. Press F5. Okay, now if you zoom in the data, you can see that you have boxes, which is refined and further refined all the way to the location down here, just to make sure that the mesh surrounding your hull having the small size of mesh, in order to resolve your mesh best. Okay, so I can open up the where is my surface. Oh yes, I need to extract first. If I want to see it, I need to extract this one. Why, what is this? So I need to extract this one. This is a compressed format, so I want to display this. So I want to display this STM file. Okay, just to make sure that your ship is the mesh surrounding your hull is the smallest one. This is some way to make sure that you have the number of cells which is as minimum as possible. Okay, in order to have your result fast. You don't refine everywhere. You just refine important location. Okay, as you can see here, the most refined mesh only created near the hull. Okay, far from it, in which we are sure that the flow field gradient are small. We don't need the small mesh. Okay, and now we have now we already have background mesh that is suitable to apply your ship. Okay, so next, our next step is to do what? Okay, so we are not going to repeat this step again, so we just put inside the comment. Okay, and then we apply snappy hex mesh. Okay, so what is snappy hex mesh? Okay, if you open up the tutorial, okay, this part. Okay, I hope you can read the details of this. Okay, this is the concept of meshing. Okay, but the specific details we want to understand is snappy hex mesh utility. Press this one. Okay, so we need to wait a bit. Why it is not there? No longer available. This one, okay, but not this one. Why? Okay, this one. Okay, so just now we have a hull shape which is currently in the STL surface format. Okay, so what happened is just now we create our background mesh using block mesh, and then we are going to use SnappyX mesh to snap the body shape into into this background mesh. Okay, so what will happen is the first step, the SnappyX mesh utility will refine mesh around the features. Okay, and then it will create a mesh around the features. Next, it will remove the mesh that is located inside the STL file, the body. Next, it will snap. Okay, it will snap the body. Okay, it will move. Okay, as you can see here, the nodes, the node is still, some protrude the body, some located outside of the STL file. Okay, so the nodes will be moved so that it is attached exactly on the body. Okay, and the next step, you will create the boundary layer mesh. Okay, so all of these steps can be found inside the SnappyX mesh dig utility. Okay, so we double click on this, and castellated mesh. Castellated mesh means you only have up to this part. Okay, if you enable snapping, it will be up to this part. If you enable everything until layers, then you can also have the boundary layer mesh for it to be accurate. But snapping at layers takes a lot of time, so I'm going to disable it for the purpose of this tutorial. Okay, you can try to enable it to see the effect later on. Okay, we have mesh close to 1 million, right? So I'm not going to wait for 20 minutes, 50 minutes just for it to finish. Okay, now we can try running SnappyX mesh. Okay, first I need to, no need to clean. I need to retain what we have just now. I want to continue with only SnappyX mesh. Okay, and place all run. Okay, now we have to wait a bit for this meshing to finish. Okay, so just like this one, okay, you can put current process in the background by pressing Ctrl Z. Okay, so if you run jobs, okay, jobs means similar to tab lah. Okay, you have how many tabs here? You have 1, 2, 3, 4, 5, 6 tabs. Okay, so in Bash, jobs is similar to displaying the number of tabs. Okay, so you have how many tabs? 1 and 2. So paraform is running, but you can see here that all the run is stopped. Okay, so you can allow it to run in the background by typing bg, means background, and the process with number 2. Okay, then again you type jobs again. Okay, now both paraview and all run is running in the background. Okay, so currently it's creating the mesh. Okay, so while it's still process, it's still not finished yet, you can investigate what happened. Okay, by opening the log. Okay, so you can see that it is okay, already finished. It's already finished. Okay, now we can try viewing the mesh. Okay, the mesh is now already updated. Okay, before we run SnappyX mesh, okay, this is the background mesh. Okay, this is the background mesh. But once we run the SnappyX mesh, Okay, press this one and then you refresh. Okay, now you can see that the body is snapped. The shape is snapped as castellated body. This one, not this one. Up until here. Okay. If you want things like this, you use snap. If you want things like this, you enable layer. Okay. So you can check the shapes by disabling intermesh and displaying the hull patch. Okay, press apply. Okay, so this is your mesh. Okay, if you miss something, then you can focus on the object. Okay, press this one, zoom to data. Okay, this is your mesh hull surface. Okay, okay, which is close to our body. Okay. Perhaps I can reduce the opacity. Okay. And now you can see that is the surface mesh generated. Okay. All right. Next. Okay. Again, if you want a smooth surface, you can enable. You can enable inside system Napier mesh dig. You turn this one to true. Okay. To follow the object body and add layers back to true. It will take quite some time to finish. Okay, next we move to the next step. Okay, now we have snapped the shape of the body inside our mesh. Okay, and our next step is to apply boundary condition. Apply boundary condition. Okay, this part. Okay, so we need to set alpha water. Just like previously, set everywhere to be 0. And then I hope you can investigate yourself the inlet specification, outlet atmosphere for alpha water. Okay, and then for U velocity. Okay, so here we apply mu mean. So what is mu mean? Mu mean is this value, negative 1.668. Okay, so this is the velocity of the motion ship towing tank, the relative velocity. Okay, check inlet, outlet, atmosphere, and hull. And then what is the for pressure? Okay, point displacement I think is relevant for 2DUF simulation. Okay, and what is K, nut, and omega? So this is boundary condition. This fields related to the our turbulence model. As you can see inside constant. Okay, turbulence properties, we are using RAS model, okay, Reynolds average model, Reynolds average stress model, and then K omega SST. Okay, we turn on turbulence and we are going to print off the coefficients. Okay, so when we use K omega SST, we need to solve for kinetic energy and dissipation, and omega dissipation, and this is turbulence viscosity. We need to solve it as well. So each of these will have initial condition as well as the boundary conditions. Okay. What else? I think you can check the constant. G negative 9.81. Okay, in the negative z direction. Href is water level. Okay, we want to set it to be 0.244. So if we display data access grid, it is somewhere here, right? 0.2, 0.244. Okay, so the water level is at the region where the mesh is smallest. Okay. Right, next. Okay, maybe I want to display the whole mesh lah. We want to display the whole mesh. This one we display as well, but we make it to be more visible. Okay, And for clip 1, we re-enable the display of internal mesh down here. Okay, so the data we allows, we are going to the internal mesh as well. Okay, apply. Okay, so as you can see, the water level as 2.44. Okay, you can change it to change the draft. Okay, transport properties. Okay, water, same like previously. Okay, and then we don't apply surface tension. So because our object is large. Turbulence properties. Okay, we have set this. Is there any other thing to set? I think that's it. Okay. System. Okay, now before we continue the run, we might want to we inspect these values and then we change according to our need. And let's say you want to change the inlet velocity, okay, for the ship, and so on. Okay, and then we move back to all run. Okay, so let us run this one first. Okay, so what is restore 0dir? It's actually to copy. Basically, this is your default value. It will copy this one into 0. Okay. So I can run this or run. So it's a problem now. Or run. Okay, it's already there. Okay, next we run set fields. Okay, set fields. Okay, again, similar like before, we from this dictionary for set fields, we are creating a box. Okay, a very large box, but it is limited up to 0.244, which is the water level. Okay, you want to set it as 1. Okay, so if I save this one and run script, okay, you can check here. This is clip, and from this I want to, okay, this construct case. Okay, if you display, you can refresh. You should refresh first because you already modify the data set fields. Okay, now we have additional value, which is u alpha water. Now we can display it. Okay, so if I change this one to alpha water, now we can see that we have applied set fields correctly at elevation 0.24. Okay, at 0.24, negative 0.24, somewhere here. Okay. Okay, next, after you set the initial field for water region, okay, we can, okay, before we run it, we want to make use of our processors. Okay, let's say my laptop have 8 cores, so I can change it to 8 cores. Yeah. So before we run this, we have to specify decompose paradigm. Decompose paradigm. Okay, so how many subdomain do I want? Okay, so I have 8 cores on my laptop, but I don't want to use all, otherwise I can hardly do other things. Okay, I want to also use my Microsoft Word and Microsoft Excel, so I reserve some cores for other tasks. So I just want to run up until 4. Okay, 4 cores. Okay, so you must make sure that the coefficient down here also follows. So we have 2 times 2 times 1 divisions. So in x, we divide our region to 2 region, in y direction to 1. So basically we have 4 subdomains to be solved on separate 4 processes. Okay, so we save this one, then we can run this. Okay, decompose. So I'll run. Say wait a bit. Okay, now you can see processor 0 until 3, meaning 4 subdomains to be solved on separate processes. Okay, so for all of these you have specific mesh region that the processor are going to solve. Okay, so here I refresh again my data. Okay, so there are some errors because some field is not initialized. Okay, so from this I can separate into different number of box, I suppose. Let's see, BTK block colors, and cannot, I cannot. Oh, this one. So here you just understand that we have successfully separate into 4 region. Okay, and starting now you can display the data from the distribution using decompose case. Okay, so latest result is inside this decompose case. It will read not from the outside, it will read what happens inside here. Okay, so now I can move this one inside. Okay, I can this one. Next we are going to run the number mesh. The number mesh is something because you have separated your cells to 4, the number mesh can help the simulation to run faster. Okay, run faster. So I can continue running here. So basically just change the numbering of the point and cells. Okay, and finally we are going to comment. So this one will not run. Now we will run the solver here. Run parallel interform. Okay, so if I run this, press enter. Okay, this one takes very long actually. My computer, it will take 8 hours because we have a number of cells close to 1 million. Okay, so you need to wait lah. It can display the results, the log here, log interform, and check what is the current time. So currently we are at time 6 iteration. Okay, this one is steady case. We use local Euler time discretization. So now we already have 6 time steps. Okay, and let's see if we already have results that can be displayed. Not yet. Okay, so if you want to have the data to be more frequently stored, you can check. You can check this part. Which part? You can check where is it? System control dig. So as you can see here, the right interval is for every 100 time step, and currently we're not there yet. Okay, so let me put the current process that blocking our further interaction with the run, and pressing Ctrl Z, okay, and then jobs, and then you want that all run to run in the background. So we write bg2, enter. Okay, so it is running in the background. And I also can investigate, in addition to opening up this file. Okay, so this will be very heavy to your system because it always check for, we need to update the file, 25 and so on. Okay, we can also run tail. Okay, this one, the file will be very big, so you don't want to open it actually. So tail will display the remaining part of the file, the end part of the file, but you want to make sure that the value will be displayed, the change in value is displayed as well. So use this command, log interpol. Press enter. Now you can observe it. You can monitor what happened. Okay, now we are at iteration number 33. Okay, and it will take long time to arrive at 100. So I change a bit on the control dict, and I want it to write at every 10, every 10 time. So I use 10 here. Okay, so I can close this one. This one is just still, the process is still there in the background. Okay, so you can see that for every 10 time step, now you have the results. Okay, 40. Okay, we wait a bit and then we see 50 and so on. Okay, so it will display every 10 time interval. Okay, so we have our jobs, both are running. Paraform and our run script is currently solving. So if we press F5 here, okay, now you can see the results. Okay, you can display alpha water. See this one, this part, we are displaying alpha water, and and we want to view from Z minus. This one from the top, maybe Y minus. Okay, Y minus is correct. Okay, and then okay, you can press this one to display at time 40. Maybe wait a little bit more. Okay, now 60 already. Let us press F5 again. Right. Okay, 60. Okay, if we move a bit forward. Okay, now you can see the motion are already there. I can try to remove this one. Okay, so okay, now we are at time 0. Okay, I refresh this. Okay, I press next frame. Okay, this is at time 40. 40 iterations basically. 40 iterations. I just press this one. If I press at the end, 560 or 80, now you can see the flow is developing, okay? The velocity as well. Okay. So here you can see that we successfully set up the case and run the case. Okay. And inside control dict, okay, you also make sure that the simulation produce some log on forces. Okay. So you can see from this, you can see the post-processing, the forces information. Okay, let's say the drag force in X and Y and Z direction inside this post-processing. This is for force, this is the moment on the body. Okay, so basically, okay, if you start from the top, this is total X, total X, total Y, total Z force, okay, pressure X, pressure Y, pressure Z, viscous X, viscous Y, viscous Z. Okay, this is the moment on the ship, X, Y, Z. Okay, above the center of gravity, by the center of the object that you specify previously. Okay, so you can copy and paste this into Excel and plot the result over the number of iterations and check. So for our concern is the X, the X total force. So the X total force, which is the resistance of the ship. Okay, is the resistance of the ship. Okay, you want to make sure that after many iterations, the value will converge into some specific value. So this is the value that you apply. Okay, if you have model size and the value is 10 kilonewton, then that is the value. Then you need to do extrapolation that we will cover next week. Okay, so I think for the 0DOF we can stop here. Okay, we can continue later on. All right. Do you have any question? Right, you can try to watch the video later on to follow one by one and make sure you get the same result as mine. Okay, and perhaps you can enable the boundary layer mesh and other things. Okay.